Hi, this is Mengyu Li. I'm showing my homework 5 demonstration. Let's get started. The first line of code, load all the libraries, and we read our first pair of images, which is here, and then we run. We detect all the SIFT features in all of the images. Then we find all the matches, and we input our F U0, V0 to construct our K matrix and use the K matrix to convert the uncalibrated points to calibrated points. Then for the least squares estimation, we take inputs to calibrated points x1 and x2 as inputs and estimate essential matrix E using the SVD decomposition. Here, the algorithm is the 8-point algorithm described in the lecture notes and the E-matrix handout. And for the ransack estimator, we write code here, which each iteration of our algorithm uses the code from the previous least square estimation to estimate the essential matrix E based on a random set of 8 correspondences, and then evaluates how good the essential matrix E is for the all other pairs x1 and x2. Then we use the distance to the epipolars as an error mirror for each random set of 8 pairs, compute the individual residues here for all the other pairs x1 and x2, and count how many residues are lower than the consensus set, which is the threshold we set here. In this case, 10 to the -5, and iterate as many times as needed according to the probability of failure. In this case, we run 20,000 times. And I'm going to run the code. It might take a while, so let's wait. Okay, here is our inlier matches, which is doable matches because not all the points are on the same plane. They distributed quite averagely. And then we construct our epipolar lines, use plot epipolar functions here, run it. And let's see, the epipolar lines here and here are quite similar to the examples provided in the homework PDF files. And we go to pose candidates from E. This function will take essential matrix E as an input, and then it will output four solutions for rotation R and translation T. First is the twisted pairs for positive E, and another twisted pairs for negative E due to the mirror effects, and store all four solutions in transform candidates. Let me run, and we go to the construct 3D. This function will loop through all four transformation candidates C and R and all pairs x1 and x2, and solves for depths lambda 1 and lambda 2 use triangulation here, which also involves a pseudo inverse here. The output will be use plot reconstruction from the chosen T and R. As shown here, it is clear to see that the camera 1 is on the left and camera 2 on the right, which is similar to the example in the homework PDF. The last function is show reprojections. The show reprojections is to compare the image points in a given camera to the reprojections of image points from the other camera. And as you can see here, other than some noise points on the skies, the majority of the reprojection points lie on the similar corresponding area in the image, which is as expected. Now we move to another pair of images here with higher resolution. First, we run the library, we load the image, and finding all the match correspondences, then we input our K matrix using different F, U0, and V0 as given. And we run the same least squares estimation. And since it is a high resolution image, we increase our number of iterations to 80,000 with the same threshold, 10 to the minus 5. So let's run it. Still, it may take a while, so let's wait. Okay, we find all the inliers that matches here, and we keep going to plot our epipolar lines here. And after we find the epipolar lines, we get our candidates T and R from pose candidates from E, and pass all the candidates into reconstruct 3D to obtain the correct image. We need to ignore the noise point here. So we zoom in the image, which give us a close look in here. As you can see, the camera 2 position is on the left, and camera 1 position is on the right. Then we show the reprojections here. Plot. And as you can see, the majority of the reprojection points are aligned with the corresponding points. And we can also do another example with another image here, which is provided in the Piazza. It's a road image, which is quite small. We load the image, find the corresponding points, use different K matrix here, and we run the ransack, which also takes a while. So let's wait. Okay. Now we find all the inline matches here, which is fine because they are not on the same plane, and we plot our epipolar lines here. Plot. Cool. And as you can see, the epipolar lines for 2 images, and the epipoles are actually showing here and here. And then we construct our 3D, and as expected, this plot is similar as the example in Piazza, and the camera 1 position is on the back, and the camera 2 position is at the front, which indicates the object movement should be moving forward along the road. And for the show reprojections, okay, let's run it. And as you can see, the corresponding points, other than some noise points here, and on the sky, the majority of the reprojection points are aligned with each other perfectly. And that's all for the demonstration. Thank you for the watching.